Ladies and gentlemen, my name is Štumberger. I'm coming from University of Maribor. I will present you our work dealing with permanent closed-loop operation as a measure for improving power supply reliability in a rural medium voltage distribution network. This work is a result of our collaboration with grid company Elektro Celje, and results were implemented in the network. Content of presentation consists of motivation for our work, then description of the discussed network, protection system and its settings, results and conclusions. Motivation for this work was the power supply reliability analysis in the grid of Elektro Celje, where it came out that two feeders are below the average values regarding SAIDI and SAIFI indices, and that some action is required to improve the situation. Possible solutions were cabling, which was pretty costly, and the second solution was the introduction of reclosers with protection relay functionality and permanent closed-loop operation, which was 5 to 10 times cheaper than cabling. Of course, this solution comes with some challenges. The main challenges are how to provide proper selectivity, sensitivity, and reliability flow for closed-loop protection system. The discussed network consists of a transformer substation 110 to 20 kilovolts equipped with own load tap changer that supply mostly rural feeders in the form of 20 kilowatt overhead lines. Our observation is focused on two 20 kilovolt feeders. The first one supplies 23 transformer substations, 20 to 0.4 kilovolts with a peak current of 62 amperes per feeder, and the second one supplies 67 transformer stations, 20 to 0.4 kilowatts with a peak feeder current of 86 amperes. On the left-hand side, we have presentation of the network and these two feeders that build the loop number 1. This is the graphical information system presentations, and another presentation is on the schematic presentation is on the right-hand side, when you can see the loop number 1. Both feeders are supplied with feeder protection relays marked with yellow color, and in addition some other relays marked with the red spurs are introduced in the loop. Some of them are directional. Our observation is focused only on the loop number 1. The protection system, if we are talking about protection system, closed-loop operation requires directional protection relays. Proper selectivity and sensitivity of relay pairs must be provided. To do this, differential evolution-based optimization of timing coordination is performed, and in this case we use extreme time inverse IC curves. Here we have a presentation of our protection system. It consists of relay pairs. Each relay pair includes primary and backup relay. For the fault marked here between the relays R2 and R3, the primary relay pair consists of the relays number 2 and number 1. So the relay R2 is the primary and R1 is the backup relay. If we observe this fault from the other direction, then the primary relay is R R19, and the backup relay is R18. They build the relay pair number 7. Selectivity is achieved by timing coordination. The main idea is that the primary relay is intended to operate faster than the backup relay. Operation time of relay is described by the equation given here, and the unknown parameters is time delay setting TDS. Other parameters A and B depends on the inverse curve type. In the case of extreme, these values are 18 and 20. The additional time delay is set to 0, and the current is marked with the symbol I, while the pickup current settings is marked with the symbol IPU. To provide proper operation of relay pairs, we have to know that each relay pair consists of a single primary and backup relay. So if we observe this current IEC that is measured on the primary relay point, then the secondary or backup relay should operate after the time CTI if the primary relay fails. Also, the time of the operation for the primary relay must be shortened than the time in which the backup relay operates. In order to determine the values for TDS, time delay setting, differential evolution is used. We define the objective function given in the form of the sum of the times in which the primary and secondary and backup relay of each relay pair operates. And these values are summed up for all relay pairs. In addition, penalties are introduced if the pickup current is outside prescribed limits, if the primary pickup current is higher than the secondary, than the pickup current of the backup relays, and of course if the time delays between primary and secondary relays are not appropriate. Results are given for the first 4 months of operation, and in additional analysis of outages before and after the introduction of closed loop operation is performed. So during first 4 months of closed loop operation, we had 3 events. 2 events were just one span apart, and event number 3 occurred during the maintenance work where it came to the 3-phase short circuit. So the event number 1 was caused by a tree. It was face-to-face short circuit, and the event number 2 was caused also by a tree. 4 on 3 broke the conductors. These are results of the analysis. In the case of closed loop operation, 49 customers and 4 transformer substations were without supply, while in the case of radial configuration these numbers would be much higher. Also, the duration of interruption was for the events number 1 and 2 pretty short and acceptable. When it comes to the power supply reliability, indices SAIDI and SAIFI. For these three events, these indices were improved substantially. Perhaps what is more important for the network users is average outage time per customer per year. And in this case, you can see that the average outage time after the introduction of closed loop operation was just 1/4 of the previous value of the outage time. Conclusion. So the closed loop operation was implemented in 20 kV distribution network. Power supply reliability was improved substantially. The target value was 20%. Based on the presented results, the outage time per customer per year was reduced to the 1/4 of the previous value. Further improvements are possible with the introduction of the communication and exchange of messages between individual relays. This is valid for the short circuit with the overcurrent protection, as well as for the earth fault protection. In the case that these communications were being introduced, the presented overcurrent protection scheme will be used as a backup. Thank you for your attention.